In this video, we will discuss a practical case, clustering S&P 500 components. We will see the goal, understanding what we obtain by grouping companies. We will explore what data and technical analysis features we can use and learn how to apply an algorithm to the data. Then, we will train a model and evaluate it, and finally we will modify the model to obtain better results. First, the goal. Our goal is to retrieve data from the constituents of the S&P 500 and calculate some indicators that, as technical analysts, we believe can have predictive value. In this case, we've chosen a transformed moving average, that is, the distance from the moving average to the price, and RSI, and ATR, the ROC, and momentum as features. However, other indicators and features, such as technical analysis patterns or signals, could also be used. Depending on the situation of the selected technical indicators, we want to group the companies. In the image, we've thought about forming 6 clusters, and we've assigned a descriptive name to each one: runners, consolidation, reversal, high volatility, low volatility, and cross. Second, what data do we need? 1. The first thing we need is to retrieve the components of the S&P 500 from our data provider. 2. After that, we'll need a historical data set, in this case daily, but it could also be hourly data, 15-minute intervals, or any other period. The historical data is necessary to calculate the technical indicators as the predictive features. 3. To better illustrate this, we will only look at the last day, which in our example is June 12th, but this calculation would be done for every day in the historical data. Now let's look at the indicators we calculate. Pause the video if you need to see the explanation of any of them. The moving average, the relative strength index, the average true range, the rate of change, the momentum, and a DOS. Remember that these calculations are done for all 500 companies each day in the historical data. Don't worry if it seems like a lot of calculations. With simple computers, this is quite manageable. A side note, don't be surprised to see 503 components. The S&P 500 can have a different number of components than 500 due to mergers and acquisitions, corporate spin-offs, temporary replacements, and special considerations by the managing committee. We will now combine all the data into a single table. Given the historical data for 503 components, we obtain nearly 370,000 lines or examples for the algorithm to learn the patterns. Although we covered this in the lecture label selection, the key to unlocking the power of machine learning and technical analysis, remember that a moving average cannot be used directly because training with prices at 170 is not applicable to prices at 120. That's why we transform it into the distance from the average to the price, a universal metric that we can always use. In the image, you can see the difference between the moving average and the percentage distance to the price. Logically, we eliminate the original moving average feature. The steps of the pipeline are not exactly linear. Algorithms influence data. Data influences algorithms, and both influence the model, which in turn influences both. For now, we will use the k-means algorithm. Later, we will explain why. We will work on feature engineering and feature selection. Generally, we like to observe if the data is stationary or not. This means if it changes over time or not. Some algorithms require the data to be stationary to model correctly. Be careful not to confuse stationary with seasonal, especially in languages like Spanish, where a stational and a stationario are very similar. A time series is stationary if its statistical properties, such as mean and variance, are constant over time, but a time series is seasonal if it shows regular and repetitive patterns at specific intervals, such as daily, weekly, or monthly. Correlated data implies redundancy, and it is generally better to eliminate this redundancy. Since k-means works with distances, scaling the features to handle similar magnitudes is crucial. Otherwise, the model results would be disastrous. Additionally, we can reduce dimensionality with unsupervised techniques like principal component analysis, or PCA, which helps eliminate redundancy. And we can use feature selection techniques. But we cannot delve into feature selection techniques at this point because there are hundreds of possibilities, and gaining experience in this area requires extensive practice. As we see, the dataset consists of data from one company after another, in blocks. Therefore, to observe the stationarity of the series, we must do it company by company. We cannot mix them. Thus, we find that almost all are stationary in all indicators except for the ATR. However, with almost 50% of companies being stationary, we decide to keep it. Performing this test in Python is very simple and takes just a couple of lines of code. Now let's look at correlation. In traditional algorithms, eliminating correlated features is crucial to avoid redundancy and bias. If momentum and ROC are 99% correlated, it makes no sense to keep both features. Again, do it company by company. We see that in almost all companies there are identical correlations, such as between the moving average and ROC or momentum. We eliminate the correlated ones and keep moving average, true range, and ADOS as technical indicators that we expect to have explanatory power. In this case, we are clustering, so we don't use labels. The algorithm does not predict but creates clusters. With our features, the k-means algorithm must find the patterns that define the groups. Remember to maintain the same magnitude of the indicators so it can compare them correctly. Therefore, we proceed to normalize the data. Again, in Python, this can be done with 1 or 2 lines of code. Additionally, we will add the returns of the next day, not to use in the clustering but to evaluate each group later. We will do this seeing if there is a trend in the returns, whether upward or downward, in each group. We review the data because remember, we are always extracting behavior or modeling the data. Any anomaly can render a model useless. This is the most tedious part of the process, but it is equally necessary. Observe how the image changes by eliminating a single anomaly from nearly 400,000 lines. In these graphs, we compare the indicators 2 by 2, showing in red the days that fall and in green the days that rise. At a glance, it is difficult to see a pattern, but can machine learning help us? Although we have already hinted at it, clustering is unsupervised learning or pattern extraction. That is, without labels or targets. The algorithm simply analyzes the data and draws conclusions about how they are organized. In this case, Megan is responsible for building the model, and she faces the decision of which algorithm to use. She knows there are different algorithms for clustering, and each depends on the nature of the data and its distribution. After discarding dbScan and others, she thinks that k-means is the best choice.
K-means works well with continuous numerical data, like technical indicators. It's efficient in computation time and scalability, and it's easy to interpret and apply. But we must establish the number of clusters as an hyperparameter.
What is an hyperparameter? Drawing a parallel with technical analysis, it would be like considering the moving average as the algorithm and the period, 7, 14, or any other value as the hyperparameter. In the same way, in machine learning, algorithms require hyperparameters that are parameters set before training the model. You will understand it well with an example. If you use k-means, you must set how many clusters to use. For the k-means algorithm, the number of clusters is a hyperparameter and is not calculated by the algorithm itself. On the other hand, model hyperparameters are calculated and optimized by the model itself as it trains. Once K is selected, the K-means algorithm finds the best way to divide the data into K clusters by adjusting the positions of the centroids and assigning data points to the appropriate clusters. This is the model fitting process, but the number K itself remains fixed during this phase. However, just because K-means requires the number of clusters does not mean we have to decide it completely manually. On the contrary, there are methods to decide the number of clusters. One of the most well-known is WCSS, or within cluster sum of squares, which measures the distance between points. In the image, the distance in WCSS are greater in the green and blue elements than in the red ones. The within cluster sum of squares. As we increase the number of clusters, becomes lower and would reach 0 if we had 503 clusters. But then it would be useless. The elbow method automatically calculates where the reduction in within cluster sum of squares is no longer worth it, or, in other words, does not exceed the minimum threshold we accept. John has observed that the elbow occurs at 8 and logically asks us,
so should we use 8 clusters?
But Micah, who has more experience, adds,
the elbow method is a general criterion widely used in machine learning. I suggest that we analyze the clusters with the asymmetry of the returns of the day.
Don't be intimidated by the phrase. It simply means if a cluster has a bias towards winners or losers. That sounds interesting.
We should use skewness as a measure of the asymmetry of the distribution of returns. But be careful. Skewness alone only measures a symmetry relative to the mean. What interests us is the asymmetry, but relative to 0, so the winners and losers, regardless of the mean.
Okay, got it. If you use Python, adjust your code.
A positive skew means the distribution has a longer tail on the right side, indicating more high-value outliers, which could suggest potential opportunities for long trades. A negative skew means the distribution has a longer tail on the left side, indicating more low-value outliers, which could suggest potential opportunities for short trades. So, although usually a 5%, 10% threshold range is a good option, we are interested in a lower threshold, like 4%.
Following Micah's advice, we have adjusted the threshold, or the level at which it is no longer worth reducing the within cluster sum of squares, to 4%, resulting in 26 clusters. In other disciplines, this would be a very low threshold, but in ours, it is necessary. Now let's look at the 26 clusters generated by the model. Don't be surprised if some presentations show 0 to 25. Python, widely used in machine learning, starts counting at 0 because it is computationally more efficient. Returning to the clusters, we observe the skewness relative to 0. Cluster number 1 has a skewness of 3, while clusters 3 and 9 also have skewness greater than 1. On the other hand, cluster 14 has a negative skewness of 4.14, very skewed towards losses, suitable for short selling or other downward derivatives. In the graph, we can see the skewness of cluster 1 and, in general, an interesting behavior. Cluster 3 also shows an interesting graph, although to a lesser extent, while cluster 9 shows a more moderate skewness. What happens, however, with cluster 14? There are only 4 samples, so that negative skewness of 4.14 is not very representative. This raises alarms in Megan's model because she observes that the 4 cases are all from NVIDIA. Examining other clusters, she finds the same issue, leading her to think that generalizing based on clusters skewed by individual companies could be a bad idea. In this course, we did not want to present perfect examples where everything goes right because, in reality, these types of things happen constantly, which is part of the process, not a mistake. Models need to be optimized and rethought until satisfactory results are obtained. The logical conclusion for Megan is to analyze company by company, each separately, to have a model that tells us which cluster of that specific company is today and what skewness to expect. For example, Juniper Networks has 4 interesting clusters. Additionally, the percentage distribution is high in 3 of them, although very low in cluster 6, so it is discarded. When Juniper Networks is in cluster 0, 8, or 11, it will generate a bullish signal. It will not tell us where to buy and sell, but it will provide valuable information. In the case of Dollar Tree, there are several bullish clusters and also several bearish ones. This will be considered for trading. Perform the same process for each company. ResMed, Ansys, Jabil Circuit, Rockwell Automation, DuPont, Tyson Foods, Epam Systems, Netflix. After eliminating a couple of irregularities, which is why there are now 501 rows or companies, each company has features in the form of technical indicators that generate a specific cluster extracted from the price patterns and historical features of that company with historical skewness. In the graph, we have ordered and presented the 5 with the highest skewness, generating bullish signals, and the 5 with the lowest skewness, generating bearish signals. If we look at the summary graph, we have 49 companies whose technical indicators used as features are currently in clusters with positive skewness. Likewise, there are 70 companies that, according to these same selected indicators, are today in clusters skewed downward, generating bearish signal. What about tomorrow? Tomorrow, the moving average ATR and ADOS will change, so the situation of the 503 companies will be different, and they will be in different clusters, some skewed upwards, others downwards, and others neutral.